In probability theory and statistics, ketosis is a measure of the tailedness of the probability distribution of a real-valued random variable. In a similar way to the concept of skewness, ketosis is a descriptor of the shape of a probability distribution, and just as for skewness, there are different ways of quantifying it for a theoretical distribution and corresponding ways of estimating it from a sample from a population. Depending on the particular measure of ketosis that is used, there are various interpretations of ketosis, and of how particular measures should be interpreted. These are primarily tail weight, peakedness, and lack of shoulders. The standard measure of ketosis, originating with Pearson, is based on a scaled version of the fourth moment of the data or population. This number measures heavy tails, and not peakedness, hence, the peakedness definition is misleading. For this measure, higher ketosis means more of the variance is the result of infrequent extreme deviations, as opposed to frequent modestly sized deviations. The ketosis of any univariate normal distribution is 3. It is common to compare the ketosis of a distribution to this value. Distribution with ketosis less than 3 is said to be platykurtic. An example of a platykurtic distribution is the uniform distribution, which does not have positive valued tails. Distributions with ketosis greater than 3 are said to be leptokurtic. An example of a leptokurtic distribution is the Laplace distribution, which has tails that asymptotically approach zero more slowly than a Gaussian. It is also common practice to use an adjusted version of Pearson's ketosis, the excess kurtosis, which is the ketosis minus 3. To provide the comparison to the normal distribution. Some authors use ketosis by itself to refer to the excess kurtosis. For the reason of clarity and generality, however, this article follows the non-excess convention and explicitly indicates where excess kurtosis is meant. Alternative measures of ketosis are the L-ketosis, which is a scaled version of the fourth L moment, measures based on 4 population or sample quantiles. These correspond to the alternative measures of skewness that are not based on ordinary moments. Pearson moments. The ketosis is the fourth standardized moment, defined as where μ4 is the fourth moment about the mean and sigma is the standard deviation. Several letters are used in the literature to denote the ketosis. A very common choice is kappa, which is fine as long as it is clear that it does not refer to a cumulant. Other choices include gamma 2, to be similar to the notation for skewness, although sometimes this is instead reserved for the excess kurtosis. The ketosis is bounded below by the squared skewness plus 1, where μ3 is the third moment about the mean. The lower bound is realized by the Bernoulli distribution with p equals 1/2, or coin toss. There is no upper limit to the excess kurtosis of a general probability distribution, and it may be infinite. Under the above definition, the ketosis of any univariate normal distribution is 3. The excess kurtosis, defined as the kurtosis minus 3, then takes the value of 0 for the normal. Much of the statistics literature prefers to use the excess kurtosis ostensibly to match the fact that the fourth cumulant of a normal distribution vanishes. Unfortunately, this has resulted in a schism in which the excess kurtosis is sometimes simply called ketosis, without the qualifier. Some software packages popular among the pure mathematics and science communities such as Mathematica, MATLAB, and Maple all use ketosis in the original manner defined above, for which the ketosis of a normal distribution is 3. Other software packages popular among the statistics and finance communities including Excel and R return the excess kurtosis under ketosis function calls. And NumPy defaults to this behavior. A reason why some authors favor the excess kurtosis is that cumulants so extensive. Formulas related to the extensive property are more naturally expressed in terms of the excess kurtosis. For example, let x1, xn be independent random variables for which the fourth moment exists, and let y be the random variable defined by the sum of the xi. The excess kurtosis of y is where is the standard deviation of, in particular if all of the xi have the same variance. Then this simplifies to the reason not to subtract off 3 is that the bare fourth moment better generalizes to multivariate distributions, especially when independence is not assumed. The co-ketosis between pairs of variables is an order 4 tensor. For a bivariate normal distribution, the co-ketosis tensor has off-diagonal terms that are neither 0 nor 3 in general. So attempting to correct for an excess becomes confusing. It is true, however, that the joint cumulants of degree greater than 2 for any multivariate normal distribution are 0. For two commuting random variables, x and y, not necessarily independent, the kurtosis of the sum, x plus y, is. Note that the binomial coefficients appear in the above equation. Interpretation. The exact interpretation of the Pearson measure of kurtosis used to be disputed, but is now more or less settled. As Westphal notes, its only unambiguous interpretation is in terms of tail extremity, i.e., either existing outliers or propensity to produce outliers. The classical interpretation, which applies only to symmetric and unimodal distributions, is that kurtosis measures both the peakedness of the distribution and the heaviness of its tail. Various statisticians have proposed other interpretations, such as lack of shoulders or bimodality. Belander and McGillivray assert that the standard definition of kurtosis is a poor measure of the kurtosis, peakedness, or tail weight of a distribution, and instead propose to define kurtosis vaguely as the location and scale-free movement of probability mass from the shoulders of a distribution into its center and tails. Moore's interpretation. Moore has given a more intuitive explanation of the meaning of kurtosis. Let where x is a random variable, mu is the mean and sigma is the standard deviation. Then where kappa is the kurtosis, var is the expectation operator. The kurtosis can now be seen to be a measure of the dispersion of Z2 around its expectation. Alternatively, it can be seen to be a measure of the dispersion of Z around +1 and -1. Kappa retains its minimal value in a symmetric two-point distribution. In terms of the original variable x, the kurtosis is a measure of the dispersion of x around the two values mu plus or minus sigma. High values of kappa arise in two circumstances: where the probability mass is concentrated around the mean, where the probability mass is concentrated in the tails of the distribution. Terminology and examples. A high kurtosis distribution has a sharper peak and fatter tails, while a low kurtosis distribution has a more rounded peak and thinner tails. Distributions with zero excess kurtosis are called mesokurtic, or mesokurtotic. The most prominent example of a mesokurtic distribution is the normal distribution family, regardless of the values of its parameters. A distribution that has zero probability at countably many points on the real line and has a Gaussian shape everywhere else on the real line is, likewise, mesokurtic. A few other well-known distributions can be mesokurtic, depending on parameter values. For example, the binomial distribution is mesokurtic for a distribution with positive excess kurtosis is called leptokurtic, or leptokurtotic. Lepta means slender. In terms of shape, a leptokurtic distribution has a more acute peak around the mean and fatter tails. Examples of leptokurtic distributions include the student's t-distribution, Rayleigh distribution, Laplace distribution, exponential distribution, Poisson distribution and the logistic distribution. Such distributions are sometimes termed super-Gaussian. A distribution with negative excess kurtosis is called platykurtic, or platykurtotic. Platy means broad. In terms of shape, a platykurtic distribution has a lower, wider peak around the mean and thinner tails. Examples of platykurtic distributions include the continuous or discrete uniform distributions, and the raised cosine distribution. The most platykurtic distribution of all is the Bernoulli distribution with p equals 1/2, for which the excess kurtosis is -2. Such distributions are sometimes termed sub-Gaussian. Graphical examples. The Pearson type 7 family. The effects of ketosis are illustrated using a parametric family of distributions whose ketosis can be adjusted while their lower-order moments and cumulants remain constant. Consider the Pearson type 7 family, which is a special case of the Pearson type 4 family restricted to symmetric densities. The probability density function is given by where A is a scale parameter and M is a shape parameter. All densities in this family are symmetric. The kth moment exists provided M greater than 2. For the ketosis to exist, we require M greater than 5/2. Then the mean and skewness exist and are both identically 0. Setting A2 equals 2 meters minus 3 makes the variance equal to unity. Then the only free parameter is M, which controls the fourth moment and hence the ketosis. One can reparameterize with where is the excess ketosis as defined above. This yields a one-parameter leptokurtic family with 0 mean, unit variance, 0 skewness, and arbitrary non-negative excess ketosis. The reparameterized density is in the limit as one obtains the density which is shown as the red curve in the images on the right. In the other direction as one obtains the standard normal density as the limiting distribution, shown as the black curve. In the images on the right, the blue curve represents the density with excess ketosis of 2. The top image shows that leptokurtic densities in this family have a higher peak than the mesokurtic normal density. The comparatively faster tails of the leptokurtic densities are illustrated in the second image, which plots the natural logarithm of the Pearson type 7 densities. The black curve is the logarithm of the standard normal density, which is a parabola. One can see that the normal density allocates little probability mass to the regions far from the mean, compared with the blue curve of the leptokurtic Pearson type 7 density with excess ketosis of 2. Between the blue curve and the black are other Pearson type 7 densities with gamma 2 equals 1, 1/2, 1/4, 1/8, and 1/16. The red curve again shows the upper limit of the Pearson type 7 family, with the red curve decreases the slowest as one moves outward from the origin. Ketosis of well-known distributions. Several well-known, unimodal and symmetric distributions from different parametric families are compared here. Each has a mean and skewness of 0. The parameters have been chosen to result in a variance equal to 1 in each case. The images on the right show curves for the following 7 densities, on a linear scale and logarithmic scale. D. Laplace distribution, also known as the double exponential distribution, red curve, excess ketosis equals 3. S. Hyperbolic secant distribution, orange curve, excess ketosis equals 2. L. Logistic distribution, green curve, excess ketosis equals 1.2. N. Normal distribution, black curve, excess ketosis equals 0. C. Raised cosine distribution, cyan curve, excess ketosis equals minus 0.593762. W. Wiener semicircle distribution, blue curve, excess ketosis equals minus 1. U. Uniform distribution, magenta curve, excess ketosis equals minus 1.2. Note that in these cases the platykurtic densities have bounded support, whereas the densities with positive or 0 excess ketosis are supported on the whole real line. There exist platykurtic densities with infinite support, e.g., exponential power distributions with sufficiently large shape parameter b. And there exist leptokurtic densities with finite support, e.g., a distribution that is uniform between -3 and -0.3, between -0.3 and 0.3, and between 0.3 and 3, with the same density in the intervals, but with 20 times more density in the interval. Sample ketosis. For a sample of n values, the sample excess kurtosis is where M4 is the fourth sample moment about the mean, M2 is the second sample moment about the mean, she is the ith value, and is the sample mean. The variance of the sample kurtosis of a sample of size n from the normal distribution as an upper bound for the sample kurtosis of n real numbers is an approximate alternative is 24 n, but this is inaccurate for small samples. Estimators of population kurtosis. Given a subset of samples from a population, the sample excess kurtosis above is a biased estimator of the population excess kurtosis. The usual estimator of the population excess kurtosis defined as follows, where K4 is the unique symmetric unbiased estimator of the fourth cumulant, K2 is the unbiased estimate of the second cumulant, M4 is the fourth sample moment about the mean, M2 is the second sample moment about the mean, she is the ith value, and is the sample mean. Unfortunately, is itself generally biased. For the normal distribution it is unbiased. Applications. The sample kurtosis is a useful measure of whether there is a problem with outliers in a data set. Larger kurtosis indicates a more serious outlier problem, and may lead the researcher to choose alternative statistical methods. D'Agostino's chi-squared test is a goodness of fit normality test based on a combination of the sample skewness and sample kurtosis, as is the Jark-Berer test for normality. For non-normal samples, the variance of the sample variance depends on the kurtosis. For details, please see variance. Pearson's definition of kurtosis is used as an indicator of intermittency and turbulence. Applying band-pass filters to digital images, kurtosis values tend to be uniform, independent of the range of the filter. This behavior, termed kurtosis convergence, can be used to detect image splicing in forensic analysis. Other measures of kurtosis. A different measure of kurtosis, that is of the peakedness, of a distribution, is provided by using L moments instead of the ordinary moments.